In this part we want to discuss Ohm's law, but not Ohm's law that you know about from school, that delta V is I times R. We want to look at the point form of Ohm's law. So let's say you have some resistive material, like a conductor, and there's charges inside the material, and there's a force being applied to the charges, F, and because there's a force being applied, there results a current inside the wire, and the current can be characterized by the J vector, current density, at every point inside the wire. So the point form of Ohm's law says that it gives a relationship between the current density that's created and the force per unit charge that's acting on the charges. So J is equal to something called the conductivity of the material, which is a positive number for regular materials, and it's multiplied by the force per unit charge. Now the total force, usually you don't see this written this way in the textbook, because the force we know about and that we're dealing with right now is the electric force, and so we'll simplify this in a while and make it easier and simplify it in a bit. But in general, the force could be any kind of force. It could be a magnetic force, it could be many different kinds of forces. So this is the general form of the point form of Ohm's law. If you come to the specific case where you're talking about a charge, a negative charge in a conductor, and so the force acting on the charge is, for instance, to the left, there's electric field to the right, so the force is to the left, and the force we know is Q times the electric field, so that Q will cancel, and you get a simpler form of the point form, which is J is equal to sigma E. So you could write the point form of Ohm's law directly as J equal to sigma E, because in this case there's no other force acting on the charges. So this is then the point form of Ohm's law, that J is equal to sigma E. If you have an electric field at any point inside the wire, there results a current density at that point. Their charges start to move, charges are moving, and the current density at that point is given by a constant times the electric field. So J is proportional to the electric field. So this sigma, when it's large for a good conductor, then a small electric field can create a large current density. For a bad conductor, sigma is low value, and then J will be small for the same amount of electric field. So if we know that J is just the number of charges per unit volume times the charge of each charge times the velocity. Since the charge carriers are negative in a conductor, then the charge is minus E, where E is 1.6 times 10 to the minus 19. So we can write down then the point form of Ohm's law this way. And we can rearrange terms to get the velocity in terms of the electric field. So in another way, the point form of Ohm's law is saying that when you have an electric field created inside the wire, the charges start to move with a drift velocity in the opposite direction of the electric field, given by this formula. So this is just another way of writing things. So this is the point form of Ohm's law then. J is equal to sigma E. How do you think we could relate this point form of Ohm's law to the form of Ohm's law that you've taken in school? Think about this for a while and then continue with the next video.